All right, so um, we're using a little like just you can do it on Cloud9 as well, but they're just using a little website here because they're not doing a whole bunch of stuff in C, just this one little project. We're going to be using a thing for ARM assembly. But in any case, this allows you to write a lot of the stuff that we're doing right now. So we're having them read a couple of things in. So, please enter some number. So like we might enter in like a -7. And then so we read in that -7. You've seen the scanf stuff in here before, right? At least in the book. I don't think we've done it in class yet, but I've just hard coded stuff, I think, reading stuff in. But, oh, well, okay. So I'll read in the value, and then how many bits do you want to represent this guy in? That's the idea. And this is where we bumped into the first part of the issue. Well, it's the second part of the issue that I got talked into. You know how historically I tend to be pretty anal about saying, well, even though I don't have to say int pointer, I'm going to say int pointer. Well, it turns out had I done that, I would have been like better off last night. But by not doing that, it actually introduced another issue that I have been doing where it wasn't a good idea. So I'm going to show you both sides, both sides today to hopefully clear it up. All right, so we read in some number of bits. Now, for if you remember, for 2's complement, you only encode negative numbers. So if you have a negative number like -7, you first. So if you have a negative number, if the value you're trying to convert is less than 0, go ahead and get the positive version of that. Turn that guy into a binary string of that number of bits, and I'll show you the first problem here in a second. And then go ahead and print it out. So this is basically convert from decimal to binary. Okay? And then we do the 2's complement version of that to get it into an encoded negative number, which allows us to store it as 2's complement. So when I pass this guy, so let's just assume I was trying to do a -7, but this guy got turned to a 7 here. So I pass in a 7, and let's say I wanted to represent it as 16 bits here. So a 16-bit version of a 7, because we're really trying to stay close to like what register sizes are for what we were dealing with in assembly. So I go into my decimal to binary down here. The very first thing I do is I'm going to create a integer pointer resulting from malloc for some number of bits. What's wrong with that? So I'm creating enough space for some number of bits, right? So I'm saying, I want to represent this as a 16-bit number. But the issue is that in a language, really any high-level language, we don't have the ability to store, the smallest variable type we have is a byte. So the smallest single value we can store is 8 bits. Well, I said, okay, so let's say I want to store a 16-bit number. I'm going to say, hey, give me enough memory for 16 bits. So it's 2 bytes, right? It's going to give me 2 bytes of memory. But then I'm going to start trying to fill that guy up with 6. So if we're doing 16, I'm representing each of my bits as an int, which is 32 bits. So I can't even store one int in my 16 bits. Yet I try to put 16 of them in there. Because a bit is 1. An int is 32. I've only created enough room for 16 bits, when really for 16, I need 32 times 16. So I needed 512 bits of space. But I only asked for 16 bits of space. All right, and this all came from, so I can say it was a student's suggestion, but he suggests, you don't need to do the size of thing here if you say it's an int pointer, but that's not true. So historically, I would have said, I want 16 times the size of whatever thing I'm storing in there, right? And we're storing an int in there. That's what we're actually going to store. It's not the most efficient way of storing a 0 or a 1, but it's how we're going to store a 0 or a 1 in this. All right, so I wasn't creating enough memory, and then we were getting all sorts of you get this malloc exception, it was breaking. And didn't know why. And then what became even more interesting, and this is more evidence of, so if I just go back here to where it was just a second ago, we'll leave it like this. I go ahead and run this in here. And what we saw there, because actually it worked for smaller values. If I use like nibble size values, 4 bits. So if I say I want to do a -2 and I want to store this in 16-bit space, I get this error message guy. Now, the exact same program, I copied it over here. -2, 16 bits, actually gives me a result. Not the right result, but a result. So, you know, the punchline is that when you're dealing with different compilers in C, they might be playing with by different rules over the decades. You might be getting some different results. So I guess I'm not necessarily sure what's the best thing to tell you other than it's the first part thing I would say here is always be explicit. So let's say that first, but then I'm going to show you in a minute how being explicit actually made me introduce something to you that wasn't accurate with today's compilers. All right, so we would have said, so what I should have said here is I want to take bits times size of int, like that. And I'm going to go ahead and steal that. So I can use it in a couple other places. So now I've asked for enough space to hold that guy. Same thing up here. Bits times size of int. Bits times size of int. Bits times size of int. I think that probably fixes it for at least now. If it doesn't, it's not a big deal. I've already kind of told you what the scoop was. Yeah, so. All right, so now this gives me the right answer. Some of this other stuff here is like error checking, like why isn't this working? Stuff that we were printing out, okay? So does everybody get what we just did there? I wasn't requesting enough space. In fact, I was trying to store 16 of something that I didn't ask for enough memory for one of. I can only store half of it. So I was 32 times short of what I needed. But now where it gets interesting then on the backside, and let's go actually into our project here, and I'll show it to you through. I don't really want to do that. I want to do maybe this, and this, and this. All right, so I want to look at an integer array again. Because we really did luck out by not having a problem with our insertion sort. Because of whichever default flags are set on the compiler for Cloud 9. We were certainly walking in interesting places in memory is what we were doing. All right, so let me kind of show you that example for a second. Most of this other stuff is... Actually, I can go ahead and show it in terms of our remove vals that we never finished writing. So let's go ahead and write that. Actually, let me show it to you in integer array here first. So I'm just going to go ahead and I'm going to just wrap all this stuff here in main in just a big old comment. So it's just out of the way for right now. Okay, so now what I'm going to do is I'm going to create an integer array, just for sample. So we'll say int pointer AR is equal to, now you do not have to specify that you want this guy to be an int pointer, but like I've said, I've always done that. So I'm going to say I want to get a pointer for an integer, and I'm going to use malloc to get this guy, and let's say I want 100 things. Now if I only ask for 100 here, I'm asking for 100 bits. So I want 100 times size of int. All right, so now I get enough memory to hold 100 integers. Make sense? All right. Now, do we have, we were doing some stuff with random numbers before, right? Was it just rand mod something, and that gave us we used to use rand mod 100, that gave us a number between 0 and 99, right? Okay. So let's just do that real quick. So we'll say int I for I is equal to 0, I is less than 100, I plus plus. So now we're going to say the value that lives at AR plus. Now, the way I've been writing it is I plus size of int to take integer size steps, right? That's how I've been describing it. So I've been saying that will take integer size steps. And we'll go ahead and fill this guy up with rand. Actually, isn't it rand 100? Will that give me the number between 0 and 99? How'd the rand function work? And rand. No, you use the mod. Okay, so it's rand. Mod 100 will give me number between 0 and 99. So I'm going to go ahead and fill that array up with that. And then I'm going to steal that same for loop. And we're going to print the contents of that array out. Printf %d, I'll just put a space after it, comma, that value. And then we'll do a printf \n at the very end to kick it down a line. All right, so build my array, filled up with 100 numbers, 100 random numbers, then spit out those 100 random numbers. All right, and let me go ahead and save that. All right, so there's my 100 random numbers. So we'll look at that, we'll think that, oh, everything's fine. Everything's been fine. Now I'm going to do a little change here. I'm going to say just plus I there. Plus I. Okay, that should do enough. Okay, seemingly gave me the same thing. So we might look at that and initially say, oh, they're just identical. You don't need the other thing. But actuality, this is the correct way to write it today. Go to my base address and add this to it. That'll take the correct size step. Remember I was walking through along the thing here the other day saying, if you need to take a char size step or an int size step, and it would be 4 bytes, a char would be 1 byte. That's all accurate. So all the things I said was accurate. But if I say here that I want to store in AR at position I times size of int, what I'm doing is I'm taking an int size step and multiplying it by an int size step, taking a 16 byte step. So I'm going way off the end of the memory that I reserved. And I just happen to not be bumping into dangerous things. Well, then we would say, well, why does it look okay on the other side? So here, let's actually write it like this. So I'll fill it this way, but then I'll print it this way. It closes. I'm missing one closing one there. Maybe I wasn't missing closing one there. Closes there, closes there. Yeah, that closes that. FAR plus I. Let me just look at what the error message says now. Int. Oh, I've misspelled. This is lowercase o. All right. So now we see our footsteps a little bit clearer. So here's a random number. My next random number doesn't occur until I've taken an extra 4 bytes of steps. Because the way I'm printing here is I'm doing plus I when I'm printing it out. When I'm filling it, I'm saying plus I times size of int. So I'm filling it here, and here, and here, and then when I'm printing it, I'm walking here, then here, then here, then here, and every now and then I bump into another random number. Now, what's interesting here is you would expect in a modern operating system, and this is where I've gotten kind of confused with this, and I don't have a good answer for you. I'll just throw it up to the cop-out of the compilers play by different rules, which is a true story, but that's not a great excuse. I've clearly walked off the end of this array by a lot. Okay, I just ran off the end of the array, and I'm dancing in memory that I did not reserve. You would hope that a modern compiler and a modern operating system would not be happy with that. In Java, we've been used to, for years, Java screaming at us and saying, string index out of bounds exception if we walk 1 bucket off the end of a string, right? It's flipping out. I've gone 20 bytes off the end of my array. I'm just dancing in unclaimed territory. This could be in the middle of another program. We don't know. Just somewhere out there writing stuff and printing. The printing stuff, that's okay. You should, as long as it's not protected memory, if you want to print whatever's at memory address XYZ, that's fine. But to be able to change that in an area where I didn't reserve it, I have to think it's got to be, it has to be luck. The way that it has to be, I guess, sensical luck. The way that the compiler is likely written here is that when it reserves the memory space for your program, it goes ahead and reserves kind of a basic heap space and says, here's the memory we're going to reserve that you're allowed to use for this program. If that's not enough, you're going to have to give us some extra flags and we'll kind of loosen the reins a little bit. So it goes ahead and kind of grabs a chunk of memory and just reserves it for the runtime of your program, almost to protect the rest of the operating system. All right, so now you have this amount of heap space. Now we've only requested this first chunk of it, but I decided to keep dancing out in here anyways. Nobody else had requested that memory, so we're kind of like, okay. We probably could play a game here. We won't spend the time doing it. We could probably play a game where we try to request a whole bunch of the memory and then fill it with like random stuff and see if we can start bumping into some of our random stuff so we're not getting zeros in here. We're instead getting like, A's and B's and question marks and stuff like that because we're just printing out what was at that memory location. And what was at that memory location by default, it looks like they filled the entire heap up with zeros. Well, I like that effect. I wonder what the purpose of that is, but I like it. But yeah, very, very interesting. We would have expected that to give us an error. And maybe the thing that's more troubling to me, and I maybe won't investigate it much more because I'm afraid I might be wrong. I wonder if for a long time I've been writing it this way and just lucking out by dancing through memory in some dangerous places. It's entirely possible. But I would have thought that there would be more oversight. But I think maybe some of the built-in mechanisms in our modern operating systems that protect the programmer from themselves, because when I first introduced like C and C++, I mentioned these languages empower the programmer to make poor decisions, right? Because it gives you direct access to memory. So, and I remember when I was first learning C years and years ago, so I could always use that as my backup plan. Well, I haven't written in C in a couple of years, so I can use that as my, and I'm old and all that other stuff. But, when I first learned, was writing C years and years and years ago, it was a thing that if you had a bug in your program, your machine might restart because you overwrote part of the operating system in RAM. So you got to make sure you save often because if you didn't, it was common for you to have to wait for reboots while you're working on your homework is what I'm kind of getting at here. That would not be the case today. Today, you've mentioned, you've seen that you've had your programs give you segmentation errors and stuff like that. Like it just bails out. Something bad happens, but it's almost like the equivalent of a try-catch in Java where it says, that we got you. You screwed up really bad. We're going to give you a really cryptic error message that is almost meaningless. Okay? But the machine did not reboot. So I'll give you the big thumbs up. I guess the punchline there is it's almost like I'm the victim of modern technology because it didn't make me run into a problem. It gave me too much wiggle room in there. I was able to just dance around in memory doing whatever I wanted just because of the nature of the small problems we were solving, and it didn't run into problems. I just found that very, very fascinating. And of course, I did this on purpose as an exercise for the classes. Still waiting for my first bug. It hasn't happened yet. This doesn't count. This does not count. In any case. All right, so does that make some sense? The deal there? So do not, where are we at here? Do not do this. Don't artificially make bigger steps than you need to. Let the modern compiler say the size of the step that you need is you want to take a step of size I off the base address, and it will know that that base address is storing integers. Therefore, it will take integer size steps as it's walking away. That make sense? So now we should have, well, there is a possibility of having a 0, but we should have far less zeros. Well, didn't have any zeros, so at least I don't see any. Whatever. All right. That make sense? So, important lesson. All right, so now let's go and solve our remove vals. And then we'll start solving the file IO thing. If we don't get to that, I'll finish solving on Monday. I won't give you homework over the weekend. I'm going to give you a little something to read. But that's I'm sorry for giving you some bad information. So if you have a good weekend, you can thank me for that.
Thank you.
What? You haven't had a good weekend yet.
I know, I'm going to have a good weekend.
But again, it was not a bug. I did this on purpose. This was the punchline you finally experienced in class today. Learning exercise, exactly. And that's how it felt last night on hour 4 of class. When we're all staring at this thing, because there's one other guy in that class, in the grad class last night, who's had quite a bit of C background. And we're just staring at this. And it was actually like a perfect comedy. Because he's got pretty recent C background. So he's here constantly telling me, oh, you don't have to put that, you don't have to put that. So he talks me into it, basically, not putting the bits times size of whatever, because I just didn't think anything of it. You know, where historic, I would just always put size of whatever. Just I always default to that. So I'm thinking, oh, well, that's being careful. Well, really, I was being bad on the other side of the equation. But this time it was his fault. But it taught me about the other problem. So we're just sitting there like the monkey doing a math problem for like an hour. Like, why is this doing it? Then it makes it even worse when you're testing it here and then you're testing it here and you're getting 2 different results. It's the same code. And it's presumably the same compiler. We're using GCC on both of them. Very interesting. And actually, didn't we have an issue last week where you were getting a different result? Oh, that was with string copy, though. Yeah, you happened to be. So that made sense after the fact. Yeah, I don't know. That made it extra infuriating, but fun at the same time. But that's at 10 o'clock at night, and you only have so much fun after you've been sitting there for 4 hours talking to people. All right. All right, so let's look at our remove vals then, since we didn't write that last time. So this guy's going to take in a string and the length of the string, and we're going to go through and we're going to build a brand new string capable of holding all the vowels that are in that string. Now we know that our new string doesn't have to be any longer than the current string, right? Okay. So we'll write this guy first. So we're going to go ahead and create some new memory here. So we'll say char pointer answer is going to be equal to the char pointer version of malloc, and we want to get length. Now, in this particular case, you probably could just say length because chars are of size byte. But Don't do that. Length times size of char will ensure that you get the correct amount of memory for whatever a char is on that operating system. And that probably becomes more and more of a thing today. I think we saw sometime earlier this week, somebody print out that chars actually were 1 byte in size, but it would be completely acceptable for a char to be 2 bytes, to be 16 bits. In fact, most modern languages use 16-bit chars because it uses Unicode. So the fact that it's using a 1 byte char probably has a lot to do with some default flag in the GCC compiler, running it as an older C99 version of it where ASCII was the cool kids thing, right? So this is safe because this then makes your code future-proof, presuming there's still a size of function that will tell you how big a char is on this system under this compiler, that type of thing. Okay. And actually, just to clarify there too, it is the compiler that's making that decision. Because remember, we're writing here in this high-level language. So when we shove that guy through the compiler is converting it to the low-level equivalent. It's the compiler that will look at this guy right here and say, oh, you want to know what the size of a char is? Let me go look that up for you. So I make sure I give you the correct value because I'm going to be converting that into the assembly code that's the equivalent of this. And at that point, memory becomes very important, which makes it even funnier that it allowed me to just dance around in memory like it did. But then I got the really, see, I don't get those. That's the thing. Without all those zeros in there, I don't get the cool little effect. That's why I did it.
If you highlighted 39, would all of 39s be highlighted?
If you're right, I'm going to be upset.
Yes.
Now you just earned homework. It was way cooler before because there were so many zeros. With so many zeros, it had an artistic effect. Okay. What was that? Okay, so we have our new char array. This is going to hold our answer. We're going to have to go through this chart. We're going to have to go through our old char array and try to identify vowels, right? And did we write anything in here that allowed us to find particularly? Did we write like index of? Yeah, we did. So we wrote index of. So if I give myself a string containing all of the vowels, I can then call that with index of, passing it the char I'm currently looking at, and it'll return me a -1 if it's not in there. Okay, so I already have a little tool I can use for this. So I will go ahead and I'll create a char pointer called vowels and set this guy equal to A-E-I-O-U, A-E-I-O-U. All right, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those guys. Okay, so we're going to go through every bucket of answer, but we're only going to keep, every bucket of S, but we're only going to keep the ones that are not vowels. That is the ones that return a -1 when I look at index of in there. So I'm going to have to keep track of two different variables. One is where I am in S, and the other one is where should I put my next guy in answer. All right, so we'll go ahead and we're going to have an int pause is equal to 0. And if we want to maybe actually keep it to even, let's call this guy answer pause. That's where we are in answer. And then we'll have int I for I is equal to 0. I is less than length I plus plus. So this for loop is going to go through every element in every element inside of S, but we're only going to keep some of them. So now we're going to ask the question. We want to know if, when I call index of, passing it vowels, and this, does it take length next or the value thing I'm looking for next? I think. Yeah. No, length. And we decided vowels of size 10. You'd probably want to put that in a variable somewhere, but whatever. All right. And then I'm going to pass it the character I'm currently looking at. So I'm going to say the value that lives at S plus I. We do need to make sure we build our memory the correct way first, since I'm now doing this in a different way. So S plus I. Oh, actually, it didn't break us for strings because we lucked out that strings were size 1 byte. 2 times 1 will always be 2. 3 times 1 is always 3. So because we were working in a system where the size of a char is 1, the difference between s plus I and s plus I times size of char is nothing. By sheer luck. All right, so this is the correct way of writing it. All right, so I'm looking at the value that lives at this memory address, which is the current character I'm looking at in S. I'm going to check to see where that guy lives in vowels. I'm letting them know that vowels has a size of 10. This is going to return an integer, which is the first index in there where that guy is found, or -1 if it's not in there. So if this guy returns a -1, that means the character I'm currently looking at is not a vowel. Therefore, I want to keep it because I'm removing vowels, right? So I'm keeping non-vowels. So I'll go ahead and say the value at answer plus pause, plus answer pause, is equal to the value that currently lives at S plus I. And then I need to say answer pause plus plus to move on to the next answer pause. So because I've determined that this guy is not a vowel, I'm going to go ahead and put him inside of answer at position answer pause, and then I'm going to increment answer pause. Now, one thing you want to be careful of if you're reading somebody else's code, and this goes back to when I first showed you some of this stuff, that is legal. Don't write it that way. This will work. I'm saying go to the position of answer plus the value of answer pause, but increment the value of answer pause after I get its value. So I'll get its value right now, but I'll still increment it because I know I need to increment answer pause after I've placed something. This is not good programming to save one line. That's a very confusing line to read, right? Unless you know exactly how the plus plus works, whether it's before or it's after, this is a confusing line to read anyway. And even if you do know what that means, you still got to stop and think about this for a second. Whereas if you just put it on its own line, life goes on. Pretty clear logic now, right? Okay, so this will go through, checking each element of S. If it's not a vowel, we'll keep it inside of answer, putting it at position answer pause, and then kick it to the next line, which is the next place in answer pause that we want to have. When this for loop is done, we have filled answer pause up with all that stuff. Now there's one last little, actually, I think it will actually happen because we will read in that \0, so we don't actually have to artificially put a \0 on the end of that string. But I think we saw before that it fills the rest of the string with \0s for the termination character. I think this would probably work just as is. Let's test it real quick, but then we're gonna make it more complete. All right, and this guy's going to ultimately return answer. All right, so we'll come up here. I'll get rid of this stuff. And we'll go ahead and say char pointer S is equal to hello. And since we're not changing it in memory, we're okay with this. We can use the literal thing this time, right? I'm giving myself a brand new string. And then we'll say char pointer answer is equal to remove vowels. We'll pass this guy S and we'll pass this guy 5, the length of that guy. And then we'll do a printf %s \n answer. Well, that's the way I always spell it. Then I just wait for the error. And then it's a tradition. I think I've been keeping track of the numbers pretty well. I think I'm spelling printf that way about 60 or 70% of the time. Way over half the time I misspell it.
I kept trying fprint for some reason.
Fprint? That's worse.
Yeah.
That is worse. Well, that makes me look way better now.
I mean, I got prints going.
Oh man, you know what keeps creeping me out? You're on the wall out here, the picture artsy stuff, and I mean it's like a Slender Man type look. I mean, I walk by and I don't know. It's maybe something. Did you make that, or did somebody use your? Is there something artistic that you're doing there where it's like supposed to like scare you, like jump out at you?
I mean, it was like my first time using Photoshop, so.
So I'm walking down the hall, and
like
then not
saying,
until
"Oh,
you
I
get to a
wasn't
certain
expecting
angle
it."
do you even see it. But then it's just him completely. Like it almost on a daily basis. That one picture freaks me out.
I thought you were gonna say that you saw my billboard.
Well, that's what I was gonna say.
Oh, you're on a billboard?
I see I see 2 billboards with him every single weekend.
Oh, where are the billboards?
One's off 94. One's right by the Majestic in Brookfield.
Okay.
Yeah, I was gonna say it's by Brookfield.
They're all over the place.
This is the Live Uncommon.
Yeah.
Yeah, so I drive back from Madison every weekend and I just see 40 space.
And the medicine buses.
Oh, you're on buses?
Yeah.
I've been on buses before, but for eating things. All right. So let's check this guy out, make sure he works as is, and then we'll doctor him up to be more complete since we're hiding our memory shame today. Oh, I didn't prototype that guy. Oh, that was another thing that happened yesterday too, using this website thing. The first half of class, we didn't have to prototype functions. Second half of class, we did. I mean, presumably when you save this and you run it, it's putting it up to someplace else and coming down, and maybe it's went to a different machine this time that had the compiler set differently, different flag. I mean, it was academically it was a kind of a fun class, but it was there was a lot of curveballs happening during that class.
Did you change where you were replacing things?
No. The exact same code that we had into because we kind of did a little example on here, and then went back, was doing some lecture stuff, and came back in here. Same code functioned differently, and the same thing using the same button because it must have gone to a different backend. I don't know, but it was entertaining. Okay, so I need to prototype this guy. Leave it like that. You don't actually have to remove the variable name, so it'll be happy now. All right, so there's our remove vowels. It did work. The reason it did work is, and this is something we do want to be careful of, is we did end up keeping the character \0 because he was a non-vowel. So that means the last time through here, when we hit the very end of S, we grabbed that \0, noticed that it was not a vowel, and tacked it on. It would probably be safest for us to go ahead and fill in. Actually, the safest thing would probably be, if you wanted to just completely cover your butt, is at the very beginning when you first create answer, fill it in with \0s. There's actually a string. Here, it'll be easier for me to look at it here. It's called mem copy, I think. Mem copy. No, that's not the one I want, but it's something like that. Memset. Memset. Yeah, that's what I want. So we can go ahead and we can just set. We pass it in a pointer. Pass it in the thing you want to fill that whole memory up with, and then how long it is, and it will fill it up with stuff. So it's equivalent to a for loop that spins through and fills it up with whatever you want to fill it with. So it's included in string.h. I think we already have that. Yeah, we have our string.h. So right after I create my remove vowels here, I'll go ahead and I'll say memset answer, and I'm going to pass it the \0 because I don't know what the ASCII. I'll say it's I want the int version of that is, and then I'm going to pass it the length, which is length. All right, let's go ahead and run this. All right, still get the same output, but what happened here is after I created my answer right here, I went ahead and I filled in that entire memory location with a with \0s, with string termination characters. Does that make sense? So it actually then be a string. Now, an interesting side effect from that, since we're looking at weird compiler behaviors, let me do something up here. We just saw it work already, so let's just do this for a second. I'll actually probably use that printf. I'm going to do a char pointer s, and this guy will equal a char pointer from malloc, and we'll do 20 times size of char, like that. Then I'm going to go ahead and do a memset to fill that with, actually, I'm not going to do a memset yet. I'm just going to say the value at s plus, well, just the value at s, that'll be bucket 0, is equal to a h. Then I'm going to print out s. So we have not added that string termination character. I want to make sure that that's still important, that string termination character. Right, so I created this new memory. I only put an h at bucket 0 of that memory. There's no string termination stuff in there. And now we'll go ahead and printf. I'm going to assume there's no string termination stuff in there because it's possible that that's what it gives as the default value. We'll have two tries at this. So I'm hoping we get an h followed by a bunch of spaces. We won't know if we have a bunch of spaces. Let me put a character after my. Oh, yeah. You're right. Let's do an LOL. So we'll see how far LOL is from the end of our string, is what we're looking for. All right, so that's right there. So that means it was filled up. So let me do a little memset s, and we'll put a let's put the int version of an a in there. So that'll fill it up with a's everywhere. Oh, but that's not gonna help me, because that'll still run off the end of the. Oh, this will help me. So we'll put the int version of an a over size 20, and then we'll try to print it out again. And so what we should see now is an h followed by a bunch of a's followed by hello, or followed by LOL rather. Okay, so that's actually kind of funny. But now what I'll do is I'm going to say star s plus 1 is equal to \0. So I'll artificially insert a end of string earlier in that. So I should now be missing all those a's. HLOL. So what does that tell us? That if I don't do this memset thing, and I don't do the carriage return thing, that a char pointer by default is filled up with string end of characters. It seems to be how it's acting, because I just created empty memory. The only thing I put in that memory was an h, yet it terminated at the end of that string as if it ran into the end of the string. So that means that because it didn't have a whole bunch of string termination, then LOL. I probably could check against. Here, we could actually prove this pretty easily. Star S plus, let's do 10, about halfway through. We'll put an E. Now, presumably, if this has already been filled up with string termination characters, then what we'll be left with is we'll have an H followed by, we'll see the same output here, H followed by LOL, because the string was terminated at bucket 1, even though I put something else at bucket 10. Make sense? So this will tell us for sure whether or not it's preloaded with string end of character. Yeah. So when you create a char pointer with malloc, the default values in there, we've seen the default values for int is 0. The default values for char is the string termination. Interesting. I'll still historically say that never trust default values, but that appears to be what the default value is there. So with that in mind, down here, I don't actually need to go and fill up my answer with the \0s because effectively this is redundant. That's what's actually happening automatically when I create it. But this would be better programming practice. If I want the whole thing to be filled up with string end of characters or string termination symbols, fill it with string termination symbols. All right. Questions about that stuff? Hopefully this cleared some stuff up that you didn't necessarily know was wrong, but maybe have been on the wrong side of the kick in the face from this. That's one of your segmentation faults. All right, so we'll look at the solution to the homework for today on Monday. No homework over the weekend. In fact, since we didn't make any progress, just no reading or anything. Just take the weekend off. And we'll pick up fresh on Monday.